So in the last class, what we have done is the following. Basically, we started so-called the uniform integrable family. Okay, so that means if I have a family, say xn, and if I can find a k such that limit k goes to infinity, supreme over I is in my index set, and integral over the set where say mod of xi greater than k, if this is equal to 0, or in other words, the tail part you can uniformly control, which is really less, means for any given epsilon positive, you can find a case such that integral over mod x greater than k, mod xi greater than k, integral over mod of xi dp, if this is less than epsilon, then we say that it is uniformly integrable. And then we have seen that if a family is uniformly integrable, then it is bounded in L1. But the converse part does not hold in general. We have seen that we have given one example. There we see that expectation of xn is 1 for all n. That means it is uniformly bounded in L1, but it is not integrable. Okay, in particular, if you take xn is equal to n into characteristic function over 0 to 1 by n. So you can find a k whenever you put k is fixed, then for k greater than n, I can always see that this expectation of over xn with respect to that integral with that set, it is equal to 1. So it cannot be less than epsilon. Okay. Okay, and then we have seen sufficient conditions for uniform integrability. In particular, if you see that if you have bounded in LP for p greater than 1, then it is uniformly integrable. And as I told you also that if you have a uniformly, means if it is bounded, okay, suppose x of n is bounded, then it is automatically uniformly integrable, because we are in a bounded domain. Since it is in L infinity, that is in also in all LP, and hence it is uniformly integrable. And not only that, this part you have seen that I put as a lemma. I'm not giving to prove these things because you have done it in your major theory course. This is simple, but one can also do the proof in a simple way, nothing else. This is called the absolute continuity lemma. In particular, if I have a say sequence or say random variable y, which is in L1 of omega, okay, then what I'm saying that given epsilon greater than 0, there exists a delta positive, okay, such that a, whenever I have this event with quality of a is less than delta, this implies that integral over a of my y dp, okay, this is same as I can think of that expectation of y, or you can think of mod y, okay, mod I characteristic function of a, this one is less than epsilon. Okay, that means what it says that if you have an integrable function, this part I think you have seen it in your major theory course. If you have a integrable function, then I can always find a delta, okay, delta positive whenever that measure of that set is less than delta, and if you integrate with respect to that set of your function, then that is less than epsilon. Okay, it is kind of the absolute continuity property. Is it no? Okay, the proof is simple. At least for this case, one is to use so-called the Borel-Cantelli lemma. Let's do the proof in a simple way. What I am saying that, so we need to go by contrapositive argument. Suppose this is not the case. That means I can find epsilon 0 such that for all delta this holds. Okay. So what I'm saying that if not, there exists epsilon 0 is positive, okay, and my sequence an is in my A with probability of say an, which is less than, I can put 1 by 2 to the power n, such that my these things is greater than epsilon. That means expectation of mod y a of an, this is greater than epsilon 0. Okay, and this holds for all say n greater or equal to 1. I can think of in this way. This is the contrapositive argument of this statement. So then what I have, if you look at this an, okay, so what I have, that summation over n is equal to 1 to infinity probability of an, this is basically finite, is it not? Hence now you just recall the Borel-Cantor lemma. What it says that if you have a sequence of events an, if that summation over n is equal to 1 to infinity p of an is finite, then that lim sup of an, probability of lim sup of an is equal to 0, or infinitely many of n, it is equal to 0. So this implies, I can say by Borel-Cantor, okay, that probability of h is equal to 0. What is my h? H is the lim sup of this sequence n. What is that meaning lim sup? Basically, you put say k is greater or equal to n of a k, and then take intersection is equal to 1 to infinity. Is it no? So that means since probability of h is equal to 0, so this implies I can write down this expectation of mod y and characteristic function h actually is equal to 0. Okay, so now what is your h? H is equal to the lim sup. So now I can use the Fatou's lemma with respect to this characteristic function. So by Fatou's lemma, what it says that the limit, that epsilon 0, this one is less than lim sup over n expectation over mod y given a of characteristic function over n, is it not? And now this part is less than or equal to expectation over that lim sup you can put inside over n mod y characteristic function over an. Is it not? That is the Fatou's lemma, it says. And now these things exactly nothing but expectation over mod y characteristic function over h. Is it no? Because h is the lim sup of an, and this one is nothing but the 0. That is actually we have proved it. So what we have, that epsilon 0, which is strictly positive, and that is equal to 0. So that is a contradiction. Okay, so this contradiction is because we start saying that the statement is false. Okay, so that means what it says that for a given integrable random variable, I can find a delta positive. So whenever my probability of, means for any given epsilon is positive, I can find a delta, because delta depending on my epsilon, such that integral over that a of mod y dp, that is small enough, means less than epsilon. Okay, so these things I think you have done it in your major theory course also. Okay, so this is required, actually you will see. So next actually we talk about the uniform integrability conditions or the uniform integrable random variables. So now question is, can we find a family of uniform integrable random variables? Okay, just knowing that I have given you only integrable random variable. Okay, so answer is yes, it is possible. So this is given by the following theorem. What it says that, so let x is in L1 omega 8p, means I put as L1 omega, but here I put as 8 because I try to show that if I define say yg, okay, so this is nothing but conditional expectation of x given g, okay, where my g is a sub sigma algebra of f. Is it not? So now we can think of, no, if you change your G, the subsigma algebra, then my y of G, it is a family of sequence you can think of. Is it not? So G over the subsigma algebra. In particular, later on we try to take my G, which is f of n. Okay, the filtration. So for each, if you varies n, then you can think of this is my y of n, which is a sequence of random variable. So only thing is that I am given to you x. Okay, x is a integrable random variable. In particular, we try to look at this yn, which is a Dubs martingale. Already you have seen it, is it no? Okay, so now my claim, then yg, g subset of f is a, means sigma algebra subset of a is a uniformly integrable. Okay, so to prove these things, you will see that we will use this absolute continuity lemma, means the previous lemma. Let us do the proof and then it will be clear, because this is really important. Later on you will see that if I have a uniformly integrable martingale xn, then xn I can write down as a conditional expectation of the limit given fn. Okay, you will see. So for that, this is the one important thing. So how to prove it? So you see that my expectation over yg, okay, these things is less than equal to expectation over mod x. This is finite. Is it clear? Because that mod of yg, this is modulus of that part, okay, and hence you can use the conditional Jensen's inequality. So that is basically mod of xgp, and then if you take expectation, that is expectation is the monotone, means if x less than equal to y, then expectation of x less equal to expectation of y, and from there you have expectation of mod of yg, which is finite. That means my yg is integrable. Okay, so it is in integrable. Okay. On the other hand, since it is integrable, what I can find out that probability of mod yj is greater than k, okay, for any k, for k say positive, these things is less than equal to 1 by k times expectation of mod x. Is it not? This part actually I can find out. So now my x is in ln of omega, it is given to you. So given epsilon positive, there exists a delta positive such that whenever my p of a is less than delta, this implies that my expectation of mod x Cauchy function over a, this is less than epsilon. Okay, so what I try to show that expectation over mod yg and then characteristic function over mod yg is greater than some k. If this is less than epsilon, then by definition we are done. Is it not? So that means I try to show that. So now what I have here, that since x is in L1, I have this quantity less than epsilon. Okay, whenever my p of a is less than delta. So we try to find this a, okay, such that this is less than delta. So now I'm saying that for any k, I have this part. So I can choose my k large enough, since expectation of mod x is finite, I can choose k, so k large enough such that my 1 by k expectation of mod x, this should be less than delta. I can always find, is it not? So that means what it says, that probability of this is my A. Okay, this is less than delta, and hence this, what it says, that this implies expectation of mod x and then characteristic function over mod yj greater than k. Okay, this is less than epsilon. Is it not? This is what I have. So now you see that these are the positive quantity, and what I can have, I have to show this part. Now if you start with this expectation of these things, so expectation of yg characteristic function over mod g greater than k, this is always less than or equal to expectation over mod x characteristic function over yg greater than k. Actually this is equal, because yg, that is the conditional expectation. So but since I have mod, so I can take this part, and this part is less than epsilon. Already we have seen it. So that means, so this implies that the family yg, where g is a subset of my f sub sigma algebra, is uniformly integrable. So what it says, that if I have an integrable random variable, then I can generate a family of uniformly integrable random variables. Okay. So as I said, that later on actually we try to choose this g just to be replaced by f of n. Okay, the filtrations. So that means my yn, which is the Doops martingale. Okay, that's very nice. So now we try to discuss the necessary and sufficient condition for L1 convergence, because your martingale convergence theorem gives you the convergence almost surely, not the L1ness. Now I try to discuss the L1 convergence, necessary and sufficient condition for L1 convergence. Okay, so this is the theorem. But it says that, so let my xn, this is a sequence of random variables such that xn converges to x in probability. Okay, it converges to x in probability. Then the followings are equivalent. So what it says, that xn is uniformly integrable. Second, it says that xn converges to x in ln of omega. So that means what it says, that if you have a say convergence in probability, and if the family is uniformly integrable, then it converges in L1. Okay. And whenever it converges in L1, then I have expectation over mod xn. This converges to expectation over mod x. Okay. And mod of expectation of mod x, this is finite quantity. So you see, from B to C is trivial. Trivial in the sense that if you just use a triangle inequality, then actually, so maybe I just try to put first B to C. Okay, so B implies C. How this is so? Xn converges to x in L1. Xn converges to x in L1 of omega. That is that expectation of xn minus x. This goes to 0 as n goes to infinity. Isn't it? So now if you look at this expectation over mod xn minus expectation over mod x and then take mod, this is less than equal to expectation of mod over xn minus x. Is it not? By the triangle inequality, hence you have this thing. So this goes to 0 as n goes to infinity. So B implies C is the trivial. Okay, let us try to prove it for A implies B, and then I leave you to you from C implies A. Okay. So I try to show that A implies B. That means if I have a sequence which converges to X in probability, and if it is uniformly integrable, then it converges in L1. Okay. Okay. So here, since it converges in probability, then we know from your basic probability course that if xn converges to x in probability, and then if you have a continuous function under continuous function, so if f is a continuous function, then f of xn converges to f of x in also in probability, is it not? So here we try to construct on continuous functions. So for given m is positive, I define, say, psi m of x. What is this? This is basically, okay, look at this picture, maybe then it will be clear. So this is my m, this one is minus m, okay, and then I join it, something like that. Let me. So this is a m, this one is a minus m, okay, and then I join it. So this is my origin. So these are the function, okay. This is m, and this one is minus m. So that means phi of x, this is m whenever my x is greater than or equal to m, and this is x whenever my mod x is less than or equal to m. So this is maybe minus m, this is m, okay, and then this is minus of m whenever my x is less than or equal to minus m. Whatever you can write down, that's not a big problem. Okay, so now we see that this psi m, it is a continuous functions. So since it is a continuous function, see what I have to show. I have to show is the following, that expectation of xn minus x, this one I try to show it. So these things actually I can add and subtract that my psi m of x, because here actually you see that if my m goes to infinity, then psi m x actually converges to x, is it not? So from here actually you will see from the picture. So because of that, what I try to find out these things, so this is less than equal to expectation of xn minus psi m of xn plus expectation of psi m of xn minus psi m of x, and then plus expectation over psi m of x minus x. Okay, so now see from this one, since xn converges to x, okay, in probability you have this part. So now you see here my construction of psi m, what I have, that psi m of x, or say mod x minus x, if you look at this modulus, so this is always less than equal to mod x on whenever my mod x is greater than m on this set, okay. So now this implies, if you take that expectation, so expectation of psi m of x minus x, okay, this one is less than equal to expectation over mod x, because function over mod x is greater than m. Okay, so now you see that I can find a m large enough such that this part, no, I can put less than or as n goes to infinity, so this part actually I can put as a, this is 0 because or basically less than epsilon. I can choose m large enough because x is my integrable. That is actually I try to show it. Okay. So now xn, this is integrable family. It is given to you because a implies b. We try to show it. So what is a? A is say that xn converges to x uniformly integrable. So xn is ui. It is given. So that implies it is bounded in L1. Is it not? It is bounded in L1. So now what I can have, and xn converges to x in probability. So I can use my Fato's lemma, at least xn. So then xn converges to x almost surely along a subsequence, no? Along a subsequence. That is, you have seen it. So that means what I can have, expectation over mod x, this is less equal to mean for, this is the Fato's lemma, expectation over mod of x and k, maybe I can put as a k goes to infinity, or mean for this part, this is less than equal to lim sup of expectation of mod xn. Now this one is finite because it is bounded in L1. So this one is finite. That means my x is integrable. So since my x is integrable, I can use my previous lemma. So I can choose m large enough such that this one, for given epsilon is positive, I can choose large enough such that this one is less than epsilon by 2. Is it not? So from here I can say that choose m large enough such that expectation of mod x on this set, mod x is greater than m, this is less than epsilon. Okay, this is less than epsilon. Okay, so now again xn is the family which is uniformly integrable. So I can do the similar thing else for that. We can choose large enough such the expectation of mod xn, characteristic function over mod xn greater than m, this is less than say epsilon by 2, and this holds for all n because my xn is uniformly integrable. This implies, is it not? I can choose m large enough such that this happen. So suppose here you have your m1, here you have your m2. So then maybe you can choose m1, the maximum of m1 and m2 such that this happen. Okay. So you can choose here, maybe you can choose epsilon by 2, here also epsilon by 2. Okay, so now what I have, that psi m of xn, this is converges to psi m of x in probability, because xn converges to x in probability, it is given to you, and psi m, it is a continuous functions, and not only that, it is a continuous bounded functions. Hence I can use the bounded convergence theorem. Okay, as I told you, psi m of x, and this is always less than equal to m. So it is bounded. Hence, by bounded convergence theorem, by bounded or dominated, whatever it is, convergence theorem, what I can say, that expectation of mod of psi m of xn minus psi m of x, this is converges to 0 as n goes to infinity. Okay, so now if you add these two results, now if you choose m large enough such that this one is also, this one is old, means if you have say M1, and if you have say M2 here, then take say M is equal to maximum of M1 and M2. Okay, then these two results hold simultaneously, and if you use my this part, then what I can say that as n goes to infinity, this part is less than epsilon. Okay, so this implies that lim sup of n goes to infinity, expectation of xn minus x actually is equal to or less than equal to epsilon by 2 epsilon by 2 is equal to epsilon. Okay, and now epsilon is arbitrary. So this implies xn converges to x in L1. Okay, so what we have seen here that if xn converges to x in probability and it is uniformly integrable family, then it converges in L1. Okay. Okay, and not only that, it is necessary and sufficient conditions, but I leave you as an exercise for the part 2. So there you just consider the function, maybe I put as a psi m tilde of x, which is x on 0 to say m minus 1, and it is linear on say m minus 1 to m and 0 on m onwards. Okay, that means it is something like that. So it is psi tilde is a positive function you define. Okay, so this is 0 infinitive to 0 infinity. So this is for C implies A. Okay, for that actually you will see. So now here you will see. So how the function looks like here. So now this is your suppose m, and this is your m minus 1. So up to m minus 1 you have linear. So this is a m minus 1 you have linear. Then actually it decays and then it goes to 0. Okay, so it decays and then it goes to 0. So here also you see that as m goes to infinity, so this is basically converges to x, but again also here you will see that it is again bounded. This psi m tilde is bounded by m minus 1. So you try to use a similar kind of argumentation, and not only that, this pm tilde of mod x, this is always less than equal to also mod x because it is there. Okay, so mod of x, and which is also L1, and then you try to use similar kind of argument to show that if I have convergence in L1, then the family is uniformly integrable. Okay, yeah. So actually to prove these things, actually one needs to use the following bounded convergence theorem. So it is a little bit generalization. What we know that? We know that if xn converges to x, almost surely say xn less than equal to say k, and then I can have that expectation over xn, okay, converges to, or in L1, no, expectation over x. This is the bounded convergence theorem. But the generalized things means actually what I am saying that we don't need in almost surely, but the probability sense is enough. Xn converges to x in probability, xn is bounded, then also xn converges to x in L1. Okay, so here actually one needs to use, because as I said that this is also bounded p of xn and so on. So if you use this bounded convergence theorem along with this function, then you will get the result that xn converges to x in L1 and xn converges to x in probability implies xn is a uniformly integrable family. Okay, so what is the usefulness? Because here we try to look at for the martingale or for the submartingale case. So here we have as a corollary of the previous theorem, or maybe you can think of as a theorem also. So it's a nice theorem. What it says that, so for a submartingale, the following are equivalent. What? A, that it is uniformly integrable. And B, that it converges almost surely and in L1. Okay. So how to prove it? This is simple. We will use the previous theorem. So now say Xn, which is a submartingale. So suppose A holds. Okay. So say A implies B. How to prove it? So now Xn, this is a submartingale and uniformly integrable. Since it is uniformly integrable, then what I know that uniform integrable implies it is bounded in L1. So Sukni over n, expectation over Xn, this is finite, and hence the martingale convergence theorem, what it says that this implies Xn converges to say X. Okay, almost surely by martingale convergence theorem. Is it not? So now I try to show that this is basically convergence in L1. So now Xn converges to X almost surely. That means it is automatically Xn converges to X in probability, and Xn is uniformly integrable. So my previous theorem says that Xn converges to X in L1. So by previous theorem, Xn converges to X in L1. Is it not? So similarly, B implies A. Why this is so? Here it says that Xn converges almost surely. So that means Xn converges to X. Okay, almost surely and in L1. So since almost surely, hence it is converges in probability in L1. So this implies Xn is uniformly integrable. Is it no? This is direct consequence of this C implies A for that part. Is it no? So for that case, we don't need any submartingale things and all these things. It is automatically there. So submartingale things I need because I need almost sure convergence. It is not given. Is it no? Because in my previous theorems, I need that Xn converges to X in probability. Then the following conditions are equivalent. So what it says that uniform integrability implies L1ness, convergence in L1, and L1 convergence in L1 implies uniformly integrability. So I need this convergence in probability, but here I get more. It is convergence in almost surely. Okay. Okay. So as a lemma, this is very nice. As I told you that if I have a martingale such that, so suppose my Xn, it's a martingale such that Xn converges to X in L1. Then I have a representation for my Xn in terms of this limit or the limiting random variable. Then I can write down Xn, which is equal to expectation over X given f of n. It's really a big theorem in the sense that I have a representation. So what it says only that Xn converges to Xn is a martingale and Xn converges to X in L1. Then I can write down my Xn is equal to expectation of X given Fn. Okay. So how to prove it? It is again simple. So what I have to show that expectation Xn is equal to expectation of X given Fn. Okay. So now Xn converges to X in L1. So then actually for any A, which is, this implies for any A which is in my A, okay, then xn cache function over A, this is converges to expectation over x cache function over A. Is it not? This part actually I can have. So now let A, see, x given fn, so xn is fn measurable. That means, and it is with respect to this conditional expectation. So maybe we know that conditional expectation is unique, so we try to use that part. So for any age in my fn, and also which is subset of always f, okay, this is fixed. So now for any n which is greater than this n, then what I have, because here I say that as n goes to infinity, this happen. So now my n is fixed because I have to show this one. So I'm looking for m which is greater than m, then expectation of xm cache function over A, this is converges to expectation over x cache function over A. This part I know. Is it no? So now xm is a martingale. Xn is a martingale. So this implies that expectation over xn given my f of n, this is actually equal to x of n almost surely, and this holds for all m greater equal to n. Is it not? So what is this meaning? That means integral over a, if I choose a from my fn, then it says that this is xn dp is same as integral over a of my xm dp. Is it not? So this one is nothing but expectation over xm cache function over a, and as m goes to infinity, so what I know from here, that this is expectation over x into cache function over a. Is it not? So now this one is nothing but integral over a x of dp. So now integral over a x and dp is equal to x of dp. So this implies by the definitions of conditional expectation and its uniqueness, xn which is equal to expectation over x given f of n, because this holds for all age in my f of n. Okay, so xn is equal to expectation over x given f of n. So what it says that if xn converges to x in L1 and xn is a martingale, then I can write down my xn which is as a expectation of x given f of n. Okay. So now we have seen that Doo's martingale converges almost to some random variable. Is it not? As I told you, no, that whenever I consider that x given f of n xn, so then I say that okay, what happens as n goes to infinity? So we try to look at that part. So for that we need something. Okay, let us first state the theorem. What it says, that is called the Levy's upward theorem. What it says, that suppose my x is in ln of omega, means it is an integrable random variable. Then I define mn, which is expectation over x given f of n. Okay, so this mn is a martingale, already we have seen it, and not only that, it is basically convergent, we have seen, because you see that supreme over m of mod of mn, expectation of mod of mn, this is basically expectation of mod x is finite, hence by martingale, it is a martingale, fn martingale, because it is a Doo's martingale. So by martingale convergence theorem, it converges almost surely, and then we try to find out the what is the identification of the limit. So we are saying that this converges as n goes to infinity to expectation over x of f of infinity. Okay, so and not only that, this is almost surely and also in L1. So what is your f of infinity, where f of infinity is defined by, you consider the union over Fn and then the sigma algebra, because already we know, because Fn is sigma algebra, so union may not be a sigma algebra, but consider the sigma algebra generated by that sets. So then it's a sigma algebra on that. So for that, it's a the sigma algebra you have seen. So to prove this kind of things, we need to use so-called the pi lambda system or the monotone theorem. Okay, in your measure theory already you have seen that, okay, you have defined the measure on your Borel measurable set and so on, and then how to extend it on Lebesgue measures and so on. So for there, no, you try to look at these pi lambda systems and so on. So what is the pi lambda system? Let us consider the definition. So I'll prove this theorem. Before that, I need the definitions. So let mathpal P and L, this is be the collection of subsets of omega. Okay, and the collection P is called, say, pi system if it is closed under finite intersection. If it is closed under finite intersection, that means that if AB, that is if A and B is in my pi, then A union of B is in also my pi. Finite intersection I put it, no? Okay, so intersection B is in my pi. So you see that it's not a sigma algebra. And for example, if you see this union of my f of n, Fn is a filtration, and if you look at this union, then it's a pi system. So another definition we say that L is called a lambda system if the following hold. So what it says that my omega should be in my L, then whenever my A and B is in my L, and if A is subset of B, then B difference A, it should be also in L. Okay, and it is closed under countable disjoint unions. This is same as closed under countable disjoint unions. Okay, that means if we have, say, A1, A2 up, this is in L, then union over AI over I, okay, is in my L. So it may not be a sigma algebra. It may be also sigma algebra. Is it not? Only thing is that because in the sigma algebra we have not given this quantity. Is it not? We have not given this quantity, but one can basically extend it to in this case. So the pi lambda theorem we try to use here, that is the theorem called the pi lambda system. What it says that if P is a pi system and L is a lambda system that contains P, P, then the sigma algebra generated by P, this is a subset of L. Okay, so if it is a sigma algebra L, then basically sigma of P is equal to exactly L. That is actually the pi lambda system. Okay. Okay, so we try to use here this pi lambda system theorem. So proof of Leibniz upward theorem. Okay, so what it says basically, now already we have seen that m of n, which is expectation over x given f of n. Okay, so it's a martingale. Okay, and now f of n, x is integrable, it is given to you. So x is in L1 of omega. Already we have constructed how to construct a family of uniformly integrable random variable given only a L1 random variable. So already we have seen this Mn is uniformly integrable, and since it is uniformly integrable, what we know that Mn by the previous theorem, Mn converges to say m infinity, which is maybe lim sup over n of mn in, or okay, almost surely, and in L1. Is it not? Because it is uniformly integrable, and hence I have this part, just the previous theorem. Okay, and also the previous lemma, what it says that since now mn is a martingale, it converges to m infinity in L1. Okay, that means I have the expressions for my mn. This is expectation over x m infinity given f of n. Is it not? This part already I have. And again mn is expectation over x given f of n also, because that is the by definitions, and this one is the expressions we have because mn is converts to m infinity in L1 and mn is a martingale. Okay, so what we have to show that this m infinity is expectation of x given f of infinity. So let eta is equal to expectation over x given f of infinity. We have defined this x of f of infinity. So it remains to show that eta is equal to m infinity almost surely. Is it not? Because you see this m infinity is fn measurable, hence also is in m f of infinity measurable. So my claim, what is my claim? My claim is the following, that integral over a eta dp, this is actually integral over a m of infinity dp for all a is in f of infinity. Okay, then actually we can show that eta is equal to m of infinity almost surely. For that I need to consider this pi system and lambda system. So as I said that union of f of n is a pi system. Now we try to show that these things is whole for a. So now let a, which is the collection of sets such that the above inequality holds. Above equality holds means integral over a eta dp is equal to a m of infinity dp. I am saying that this is my collection A, and then you see that this mathcal A, it is nothing but you have actually your lambda lambda system. Okay. Now expectation of eta given f of n, this is expectation over x given f of n, and this is same as my m of n. This is same as my expectation over m of infinity given f of n. Is it not? If you use this tower property, because expectation of eta is nothing but x given f infinity. F infinity is a bigger, so this is same as my expectation over x given f of n. Okay, and hence this is same as my m of n, and I have this part. That means what? That means this integral, because with respect to a f of n, so if I write down in an integral form this conditional expectation, this is exactly integral over a eta dp, same as integral over a m infinity of dp. Okay, for all a is in f of n. That means this integral, sorry, that means this integral holds for a is in fn, and hence it is for pi. So this implies my f of n is subset of this mathcal A. Okay, is it not? And now observe, as I say, that my union over n of f of n is a pi system. So that means my this union over n f of n, this is subset of A, and by pi system, pi lambda system gives me that integral over a eta dp, integral over a m of infinity dp for all a is in my f of infinity. That is the sigma algebra f of infinity, sigma algebra union of n of f of n. Is it not? This holds for a belongs to f of n. That is actually we try to show it. Okay. Now, as you see, this eta and m infinity, they both are f of infinity measurable. So what I try to show, that we try to show that the probability of this set whenever eta is greater than m infinity, it has a zero probability, and similarly for eta is less than m infinity, that is also zero probability. So let us try to consider A, the set all those omega where my eta is greater than m infinity. So now this is in again the A is a event from f of infinity, and hence what can write down from the previous one, from here what I can have, that expectation of eta minus m infinity and then characteristic function over this set A, this is actually is equal to 0, is it not? Because of here m minus eta from here I have, but eta on A, so eta is greater than m infinity, that means that probability of A should be 0, is it not? Probability of A should be 0. So that means that probability of omega such that eta greater than m infinity is equal to 0. So similarly, we can show that probability of all those omega such that eta is less than m infinity, this is actually is equal to 0. Okay, so thus my eta is equal to m of infinity almost surely. Okay, so that means what it says, that if you have integrable functions and if you define m of n, so expectation over x given f of n, then it is converges to expectation x given f of infinity almost surely and in L1. This is the conclusion. for that. So this is called the Levy's upward theorem. Okay. Okay. So using this kind of argumentation, is not exactly this kind of argumentation. What I am saying, that one can also find out the dominated convergence theorem for conditional expectation. We already have dominated convergence theorem for random variable case. Okay, so now we try to know the dominated convergence theorem for conditional expectation. What it says basically, so it says that suppose my y of n is a sequence which converges to y almost surely, and y of n is less than equal to z, where z is in my L1 of omega. Okay, under this condition, what we know, that okay, expectation of yn converges to expectation of y, or yn converges to y in L1. Is it not? That is the dominated convergence theorem. So if my f of n is increasing to f of infinity, we have defined that part, then the expectation over yn given f of n, okay, so it should converge to expectation over y given f of infinity almost surely. This is the statement of dominated convergence theorem for conditional expectations. Okay, so how to prove it? Let us do the proof. So for that, I am defining some random variable wn, which is supremum over the difference yn minus y of m, such that my n m, which is all greater than or equal to that fixed n. Okay, so now what we know, that yn is less than or equal to z, and hence I can have wn is less than or equal to 2 times z, and which is also L1 of omega. Okay, so that means my wn is integrable. Is it not? So I can use the Levy's upward theorem to say that expectation of wn given f of n. See, this n is now fixed. Okay, n is now fixed. This one is converges to expectation of wn given f of infinity almost surely and also in L1. Is it not? That is the Levy's upward theorem says that. Okay, so not only that, I have something like that lim sup over n expectation over mod of yn minus y given fn. Okay, so these things is less than or equal to limit n goes to infinity expectation over wn given f of n. Is it not? Because yn converges to y almost surely, and hence if I consider lim sup, then actually I can consider these things, and which is basically expectation over fn in this form. Okay, because this wn minus w, I have this wn definitions of w of capital N, and this part, and this is the previous one is expectation of wn given f of n infinity, because convergence in L1 implies with respect to this modulus things actually I have, because wn is positive quantity, no. So now what I have, lim sup of n expectation of mod of yn minus y given f of n, I have less than or equal to expectation of this field. And you see this w of n this decreases to 0 as n goes to infinity. Is it not? As n goes to infinity, w of n, this decreases to 0 because yn is converges in L1. Is it not? So from here actually you will see, because this is supreme of n, so as n goes to infinity, m goes, so whenever n, capital N goes to infinity, then small m and small n goes to infinity, when yn converges to y almost surely, hence actually it is converges to 0, means decreases to 0 as n goes to infinity. And thus what we see, that since now this one decreases to 0, so this part is decreases to 0 as n, capital N goes to infinity. Okay, is it not? So another thing is that by dominator convergence theorem, because yn converges to y almost surely, yn is bounded by integrable function, so by dominator convergence theorem y is in L1 of omega. Is it not? And hence I can use again the Levy's upward theorem. That expectation over y given f of n, this is converges to expectation over y given f of infinity, again in almost surely and in L1 as n goes to infinity. Is it not? So now we try to combine these things. What we have to do? We have to show that expectation over yn given f of n minus expectation over y given f of infinity. Take that modulus. So these things I can add and subtract. Expectation over yn given f of n minus expectation over y given f of n plus expectation over y given f of n minus expectation over y given f of infinity. Okay, so now this part I can put modulus inside, so this is expectation over, because conditional expression is linear, so yn minus y mod given f of n, and plus this is the modulus things, y given f of n minus expectation over y given f of infinity. So now this is converges to this part, so from there I can choose this is less than epsilon by 2, and this part you have seen the lim sup of these things is goes to 0 as capital N goes to infinity. So if you, because this is independent of n, hence actually you can find out that this is less than epsilon by 2, or in other words these things is goes to 0 as n goes to infinity. Okay, so now what we have seen, that the application of Levy's upward theorem to prove the dominator convergence theorem for conditional expectation. Okay. Okay, so far we are considering the forward martingale. Okay, that means that n is equal to 0, 1, 2 and so on. So now we try to look at for the backward martingale. So for that let us consider the definition. What it says that, so let I put as a z minus, which is minus of n such that n is my natural number. Okay, and I calculate my g of n, where n okay is negative, is an increasing sequence of sigma algebra. So that means basically what it says, that g of n is subset of g of m, okay, for n less than equal to m but less than equal to 0. It is increasing, but the index are basically from the negative part. Okay, on means on z minus. So a backward martingale I say that xn such that n is less than equal to 0. This is a stochastic process adapted to g of n, okay, with say initial, this is not the initial, now it is a final, x0 is in L1, and for all n is less than equal to -1, I have the following expectation of x of n plus 1 given g of n. This is actually xn almost surely. So this is called the backward martingale, because we have considered the definitions of martingale, but the index we are looking from the backwardness, okay, on z minus. The index set on basically on z minus. So now if we use a tower property, this is a one you can think of as a remark, that if you use the tower property of conditional expectations, then I can see, so my claim is that xn, if it is a backward martingale, then xn can be written as conditional expectation of x0 given g of n. Okay, this is my claim. How? You start with my xn. This is expectation over, okay, indeed this is x of n plus 1 given g of n, is it not? So now I am writing down this xn, I can write down this is x of n plus 2 given, 2 given g of n plus 1, is it not? Conditional expectation and then given g of n. So now you see that g of n plus 1 I am considering. So then what we have, you have g of n, say suppose g of n is equal to say g of n is equal to say -2, then this is -2 plus 1. So this is bigger one, is it not? Because n plus 1 is bigger than -n whenever it is n is positive, negative, whatever it is there, okay, in that side. So then I can use the tower property. This actually gives you that expectation over x of n plus 2 given g of n. So now you can again write down x of n plus 2 in terms of x of n plus 3 given g of n plus 2 and given g n and so on. So now what we can write down, n is lies from -n less than equal to minus of n, and then if you just add n plus 2, n plus 3 and so on. So how much I can go for, because this is all are increasing, so I can go up to x of 0. So this is, if you repeat these things, then I have x of 0 given g of n. So x of n, if my xn is a backward martingale, then I can express my xn as a expectation of x0 given g of n. Okay, so since my g is in L1, it is always integrable, and not only that, it is a uniformly integrable, because x0 is in L1 and Gn is your sigma algebra, is it not, subsigma algebra, and then already you have seen this family xn, it will be uniformly integrable, and hence it is bounded. Okay, it is automatically you see the expectation xn is the expectation of x0 because of these expressions, and x0 is in L1, so you can always have a convergence. Okay, so theorem, so let x of n is a backward martingale, then that x of -infinity I am defining as limit n goes to infinity, x of -n, this always exists almost surely and in L1. Okay, so already you can think of in a little different way. So the convergence I have to prove it first, convergence in almost surely. So for that, so suppose my u of n, which is the number of approaching, that number of approaching of AB by the sequence now xn minus 1 up to x of 0. Okay, so then the approximate lemma, what it says, that b minus a expectation of un, this is less than should be expectation over x0 minus a plus. Okay, so by using monotone convergence theorem, because un is always increasing, so by monotone convergence theorem, what I can say, that expectation of u infinity, this is finite. Okay, expectation of u infinity is finite, hence the limit actually exists. This implies limit n goes to infinity x of minus n. Okay, it exists, and let we define x of minus infinity is equal to limit n goes to infinity x of minus of n. And already we have seen, because of this expression, the xn, I can write down conditional expectation about x0 given g of n. x0 is in L1 of omega. This implies xn, this is uniformly integrable family. Okay, so now xn converges to x of minus infinity as n goes to infinity and uniformly integrable. So this implies that xn converges to x of minus infinity. Okay, in L1 also. That is a simple proof. Okay, so for forward martingale the proof is complicated, but see, for the backward martingale proof is really simple because of that expressions already we have. Okay, so xn is in L1, then I have this part. Okay, how much time I have? Oh, okay, I have time, so maybe I'll take few more minutes and then I will finish this discrete martingale part. So now I have to look at, okay, so what we have seen, that m of n is a martingale, and the stopping theorem, what we have seen, that expectation of m of t, if you have a stopping time, that is same as my expectation of x of 0. Okay, so here we will look at little bit different issue. In particular, if I consider that m of tau, where tau is any finite stopping time. So look at this family m of tau. So we try to find out this m of tau, where tau is finite stopping time. So this is a family. What can you say about this family? Whether this is uniformly integrable or not, and whether it will form a martingale or not. So since tau is a stopping time, then already we have already defined the filtration with respect to generated by the stopping time. So in particular, so if tau is a stopping time, then the sigma algebra, that f of tau, how it looks like, f of tau is nothing but all those a is in my f such that a intersection that tau is less than equal to n, this is in my f of n for all n. Okay, so tau is a stopping time, that means tau less than equal to n is in my fn measurable, and tau takes value 0, 1, 2 and so on, is it not? And f of tau, the sigma algebra f of tau is in this setup. So then, as I say, the optional sampling theorem with this completely different way. So let m, which is my m of n, be a uniformly integrable martingale. Then the family, I already wrote down, this is m of tau such that tau is finite stopping time is uniformly integrable. And not only that, I have the following relation. Moreover, for all stopping times, say sigma which is less than or equal to tau, we have expectation over m tau given f of sigma. This is actually m of sigma almost surely. Okay. M of tau given f of sigma is equal to f of sigma almost surely whenever sigma is less than or equal to tau. It's kind of it says that this m tau is basically it's a martingale. Already we know that it is a martingale, but here what it says that whenever we are writing down the martingale, that means we are looking for the basically deterministic time point, no, n1, n plus 1, and 3. But here I have my tau, so the sigma is represented by this random time now. That is not a deterministic, now it is a random time. But this is also whole. The condition is that I need the uniform integrability conditions of my given martingale. Then actually it should be whole. Not for any martingale. If you have say mn is just a martingale and then sigma and tau are two stopping times either sigma less than or equal to tau, then I cannot say these things almost surely. Okay, it is possible only when tau is when the given sequence mn is uniformly integrable martingale. Let us do the proof. Okay, and then I'll stop. This is a very nice result. So mn this is uniformly integrable, it is given to you. So this implies mn is bounded in L1. So martingale convergence theorem by martingale convergence theorem that my mn converges to some say random variable almost surely and also L1 because it is uniformly integrable. Already we have seen it, is it not? And not only that, I can have n infinity. I can write down the lim sup of n of m of n. Okay, and again, what I can write down that m of n. This is nothing but expectation of m of infinity given f of n, is it not? Because mn converges to m infinity almost surely, and hence I have this quantity. Okay, so now let tau, this is an arbitrary finite stopping time. Okay, tau is finite stopping time. Okay, means almost surely. So then this tau less than n, this is always less than or equal to n for all n is in my say z plus, is it not? Means 0, 1, 2 and so on and so on, non-negative integer. And as long as I have these things, so then f of tau cap n, this is subset of my f of n. This is the property of your filtration. One can look at this part. So now what is my tower property? That expectation of m infinity given f of tau cap n. This is the minimum of tau and n. No, I have already defined it. So this part actually I can write down that m infinity given f of n. Okay, expectation and then given f of tau cap n and then expectation. This is the tower property one can think of. So now this one, this is by tower property. Now this one, f of infinity given f of n is nothing but my m of n. Is it no? So this is expectation of m of n given f of tau cap n. Is it not? So now this one, and then n is tau of n less than equal to n. So this is, I have m of tau cap n. Okay, f of tau cap n. Okay, so now if you send that n goes to infinity, so now I define my g, which is equal to f of tau cap n union over n and then sigma algebra generated by that thing. So sending n goes to infinity, I have this part. So then what I can have from here, because this is Leibniz upward theorem, n infinity is in L1. So expectation on these things f of tau cap n, and I have sigma algebra. So what it says that as n goes to infinity, I have expectation of m of infinity given this g, no? This is the g. This is same as that limit n goes to infinity m of tau cap n. So now tau is finite, so that minimum as n goes to infinity, so I have this is actually m of tau almost surely. Is it not? So now we claim that g can be replaced by f of tau. Okay, g can be replaced by f of tau. So that means I take a, which is from f of tau. Then, because this, if I try to write down in terms of integral form, this is Cauchy function over a and m of infinity. These things I can write down that Cauchy function over a intersection whenever my tau is finite of f infinity plus expectation Cauchy function over a intersection where tau is equal to infinity. Okay, and m infinity. Is it not? This part actually I can decompose it. So what I know that m of infinity given g expectation, this is actually my m of tau. This holds almost surely. Already we have proved it here. Is it not? So thus this implies what I have, that expectation of Cauchy function over a intersection tau is finite over m infinity. This is actually same as my expectation over Cauchy function over a intersection tau is finite of m of tau. Okay, and trivially, because this part is happening because this set is in G, and then you have your exactly this part by using the conditional expectation. And trivially I have this quantity expectation of Cauchy function over a intersection tau is equal to infinity of m infinity. This is same as expectation over Cauchy function over a intersection tau is equal to infinity and then m of tau. because I put as tau is equal to infinity. This is the trivial things. So now if we add these two things from here, now I have, this implies expectation of h function over a over m of tau. This is exactly nothing but expectation of a m. Now I can put as a m of tau. All these things I have, if I add these things, this is cache function over a m of tau, and this holds for all age in my f of tau. Okay, so that means by definitions of conditional expectation, I can say this is m of tau is nothing but the conditional expectation of f of infinity, m of infinity given f of tau. Okay, so now f of tau it is again, that means my m of tau is infinitely integrable. So this implies, because m of infinity is in L1 and this is expectation of m of infinity given f of tau. So from L1 function we can generate the integrable function. This implies m of tau, where tau is finite stopping time, is uniformly integrable. Okay, so this is uniformly integrable. So since it is uniformly integrable, we will type, okay, for the second part, this is trivial, some sense. Now we have two stopping time, sigma and tau, with sigma is less than equal to tau. Okay, so this implies my f of sigma, this is subset of f of tau. Okay, so what I have to show? I have to show expectation of m of tau given f of sigma. This, by using tower property, I can write down expectation over m of tau. Sorry, m of tau already we have proved it. M of tau is equal to this part. No, expectation of m of infinity given f of tau. So this is expectation of m of infinity given f of tau. Okay, and then given f of sigma. So now this is actually, now f of tau is bigger. Okay, so by tower rule I have expectation of this is m of infinity given f of sigma. Is it not? So now again I can use this part. This is tau is just a general finite sigma finite space. So I can also put it from here that this should be same as my f of sigma almost surely. So what I have, this implies expectation of m of tau given f of sigma, this is equal to m of sigma almost surely. Okay, so basically for this stopping theorem, what it says that if you consider the finite stopping time tau, and then if I have a uniformly integrable martingale m of n, then that m of tau, the family of m of tau, where tau is a finite stopping time, is uniformly integrable. And not only that, if you have two stopping times, say sigma and tau, with sigma less than equal to tau, then I can have expectation of m of tau given f of sigma is equal to m of sigma almost surely. Okay, so I'll stop here, and then next day I'll start about the martingale in continuous time. So there mostly you will see that all these theorem follows. The idea is the following: we consider there the path continuity, in particular the right continuity path of the given martingale, continuous martingale. So that means whenever you discretize it, okay, you consider the discretizations of that. So in a discrete level, it's a discrete martingale, and whenever it is a discrete martingale, then you can apply the previous all these theorem. Okay, so and then the idea is whether you can, the discretization length is really small enough, so that you can use the continuity argument there to prove that the all these discrete results holds for a continuous setup, okay, in a nice way. So that is why we spend more time on discrete setup, because in a continuous setup all the theorems are somehow the generalization or extension of discrete lemma, because there you will try to use all these results for discrete martingale, okay, and then use the path continuity property of its path, in particular right continuity property, to prove that the same result holds for continuous time martingale also. Okay. Okay, I'll stop here. So as I told you in the exam, it will be up to your continuous the discrete martingale, not the continuous time martingale, because I want to give you some time to read all these things. Already I have uploaded the assignments in for this martingale theory. Okay, please go through it and solve it. So you don't know, maybe some questions from there it may come to your exam. Okay, so please try to solve yourself, and not only that, if you solve yourself, then you can understand what is the theorem, what are the analysis behind all these things. Okay, so you need these things. Okay, I'll stop now. Thank you.
Thank you, sir.